talking about inverse leads us to some new things. We're going to be next looking at two different types of equations. The first one's going to be the exponential. The second one's going to be the logarithmic, and those will be inverses of each other. And there are some important characteristics of the two functions that understanding inverses helps us to find. Let's review, as we move into exponential functions, some properties of exponents. Remember that if you have a base raised to an exponent, another way you can write that is as a radical, where the radical has the denominator of your exponent as its index, so the denominator and the index are the same, and the exponent on that is the numerator of this exponent. And there are two different ways to write that radical form. You can either have the exponent outside the radical, or you can have it underneath the radical. They both are the same. There's absolutely no difference between them. But it does imply a different sequence in which you do the calculations. In this first one, where the exponent is outside, that implies that you take the root first, and then you apply the exponent. Where the exponent is underneath, that implies you raise to the power first and then take the root. Normally you'd do the root first and work with smaller numbers, but both apply. So that's true for all values of m and n, and you've looked at that previously, where where m and n were always integers. I don't think you've seen any exponents that weren't at least fractions. But now we're going to extend these concepts for exponents to where the exponents can be irrational numbers. No longer do they have to be an integer divided by an integer. They can be anything. When we do that extension, that allows us to look at some additional properties. And one of those things is that if you have a number a that's positive but it's not equal to 1, you don't want to let 1 in, because no matter what exponent you raise 1 to, you still keep 1. So anything other than 1 that's positive. Then with that kind of a number, the following things are true. If I take that number and raise it to a power, then every number that goes in for x gives me a different result. It's a unique result. I can't put two different x's in and get the same result. So a to the second and a to the third are going to be different numbers. That's going to be true for every x, as long as they're real numbers. And that's what we're only going to look at real number x's now. Because of that, if we have an equation that says a to the b equals a to the c, this equation is true if and only if b equals c, which is just a result of that first statement. First statement says that it's unique, therefore a to the b equals a to the c means b equals c. Or if b equals c, then the other equation is true. This is one of those transformation type things we're going to use later to help us solve equations, is the fact that if the equation is true, then the exponents have to be the same. And the b and the c are the exponents. Third thing, if a is greater than 1, now up here we were just saying it's greater than 0, but not 1. Now we're going to say if it's greater than 1, then a larger exponent gives you a larger result. 2 cubed is larger than 2 squared. Right? 2 squared is 4, 2 cubed is 8. So if that number is, if a is greater than 1, then as you increase the exponent, you make the number bigger. Conversely, if a is between 0 and 1, it's still positive, but now it's a fraction. As you increase the exponent, you make the number smaller. 1/2 squared is 1/4. 1/2 cubed is 1/8. 1/8 is smaller than 1/4. So a number greater than 1 increase in the exponent makes the number bigger. A fraction increase in the exponent makes the number smaller. Those are just properties that we're going to use to work with the things we're going to look at next. So let's look at what we talk about if we talk about an exponential function. For an exponential function, the variable is now going to be up in the exponent. Previously, all the functions we had, the variable x was down here in the base, and we had a number a number for an exponent. But now we're going to have the variable be the exponent, or the variable, we'll later extend that to where the variable is part of the exponent. But the basic one is where it's a to the x. That's the base function. And for this one, we're going to let a be greater than 1. It's going to behave, it's going to look a little different. It's not going to behave differently. It'll look differently if a is between 0 and 1. So let's look first at where a is greater than 1. For an example, we'll use 2 for a, just so it gives us something to look at. If we create the xy table for 2 to the x, it looks like this. Plot that, and it looks like this shape. Some characteristics of that shape. The x-axis is going to be a horizontal asymptote. No matter what value we put in for x, we cannot make that function be 0. So that's an asymptote. And because 2 is a positive number, no matter what exponent I put in, I cannot make it negative. It's always going to be a positive number. So this function exists only above the axis. And as I keep increasing x, because this is larger than 1, the number keeps getting bigger. So it's an always increasing function. It also will always go through the points -1 and 1 over a. In this case, -1 and 1/2. It will always go through the point 0, 1. No matter what the base is, it goes through the point 0, 1. It will also always go through the point 1a. And so this would be 1 and 2 for this one. Those are general characteristics of the exponential function. That horizontal asymptote of the x-axis, always increasing, and it goes through those 3 points. So every exponential function, no matter what a is, will go through the point 0, 1. So I could use 2 as a base, I could use 1500 as a base, and it doesn't matter. If I raise it to the 0 power, I get 1. Remember, anything to the 0 power is equal to the number 1. That's why it always goes through that point 0, 1. A is the base, whatever number we're putting here. In this case, I used 2 for that to get this table. But whatever, I mean, a can be any other number, but it's just a fixed number for this function. What's going to vary is x. So I can either take 2 to the x, or 5 to the x, or 100 to the x, and it will look like that. The domain of this is -infinity to infinity. The range is 0 to infinity, but not including 0. It's continuous everywhere. Goes through those points. Okay. What happens, though, if the base is a fraction? The previous one was where the base was greater than 1. Now let's look at it where the base is a fraction. This time we're going to use 1/2 for our base just to get this table. When we put numbers in here, if I put a negative number in now, I get a number greater than 1, and so forth. If you graph that, the function now looks like this. And remember, that gets back to that characteristic that If you have a number between 0 and 1, as the exponent increases, the number decreases. That's what's happening here. Our number decreases as x gets bigger. So it's an always decreasing function. I still can't make the function equal 0, so my x-axis is a horizontal asymptote, just like before. And just like before, this function is going to go through the point 0, 1. It's going to go through the point minus 1 and 1 over a, and it's going to go through the point 1a. So it doesn't matter what a is. It's always going to go through those points. A between 0 and 1, decreasing function. It's continuous. The domain is, again, minus infinity to infinity, range 0 to infinity. An example of one of these exponential functions is compound interest. You looked in previous classes at simple interest formulas, I equals PRT. That's not what's used for money calculations. What's used is compound interest. Compound interest comes into play because what they're doing is if you're investing, then you're going to earn interest on the interest dollars. If you borrowed, then they're going to charge you on what's remaining every time. And so it's a compounding of the interest. It's not just a one fixed number. If you look at it as a growth thing, if you invest a principal at an interest rate of R, then after a year it will have grown to P plus P times R. So if I take the R, like a 5% interest, 0.05 times the original amount, and at the end of 1 year, what will be there is P times 1 plus R. But now for the second year, this is what's going to be growing. And I'm going to use the interest rate on that. So I'm going to have P plus 1 plus R. That's where the second year begins. At the end of the second year, I've added this much to it, which is just 1 plus R squared. And you can continue that for as many years as you want. And so the general formula is that the amount at a future date is equal to whatever was originally invested times 1 plus the interest rate raised to the t power, where t is in years. Interest rate R is in percent per year, and exponent is in years. That's the concept. It actually generalizes where the compounding can occur not once per year, but any number of times per year. And this is the more general formula. In this case, this is the amount for the future. The P is the amount started with. R is still interest per year, percent per year. You write it as a decimal, though. So interest per year. But now we're going to add a parameter N, where N is how many times per year are you compounding that interest. If you're investing, if you have money in a bank, which most people don't anymore because it doesn't help you any, but it used to be, and I guess still does technically, they compound interest 4 times a year, every quarter. That would be an N of 4 times per year. And so you divide your annual interest rate by 4, and each time you calculate the interest, you base it on R divided by N interest rate. So say you had a 4% interest per year. Then if you're compounding quarterly, every quarter they'd calculate it with a 1% interest. But you're also having more quarters than you have years. There are 4 quarters in a year, so you have 4 times the number of years as how many compounding periods occur. So you also have the T up, or the N up here multiplying the T. This is the general form that includes the compounding periods. This gives a growth from a beginning. And there are variations of that same type formula, which you can look up online. I know when I took my economics class, we wound up with a whole bunch of these types of formulas for calculating different types of things. Starting from this, what would it grow to? Or if you keep adding something to this each month, what's it going to eventually grow to when you put interest with it? So there are different variations of this formula involving future, present, interest rate, compounding periods, and time. And you can add in series of payments and so forth. All of that they begin to be fairly complicated formulas, but they calculate those kinds of things. Here we're going to limit ourselves to this formula for calculating. So this is the formula if you're investing and the money is growing. This does assume that there's been no additional money put in, there's been nothing taken out. It's just placed there and left. And perhaps something like this would be a retirement account or something that you don't touch. So suppose you had $2,500. It's deposited somewhere paying 6%. It'd be nice to get that. So, if you're in a bank right now, it's like less than 1%. So anyway, for purpose of calculation, let's look at 6%. And it's compounded twice per year. Obviously, that means you're going to do that too. So what's the amount after 10 years? And again, no withdrawals. And how much interest was earned? Remember that when you're working with interest calculations, the phrase interest means dollars. Interest rate means percent. Make sure you keep the two distinct. They are different things. So, first question, what's the amount that's in there after 10 years? So we put $2,500 in and forget about it, and 10 years later we come back, how much is there? Well, in the formula, which here's the formula right here, the A is going to be the amount in the future. That's what we're going to try to find. The P is how much you started with. That's our 2,500. So P is 2,500. R is our interest rate. Well, our interest rate is 6%, but we're going to use it as a decimal, so it's 0.06. And our N is how many times per year is it being compounded. This says twice a year, so N equals 2. T is how many years. T is always in years. N is always how many times per year. R is always interest per year. So this says for 10 years, so T is 10. Plug those numbers in, do the calculation. You need to know how to do exponents on your calculator. Exponents other than just 2. If you don't know how, ask somebody else. If you want to come ask me, I can help you outside of class. I can't tell you as a general rule because different calculators work differently. And I have to look at your individual calculator to see what has to be done on it. But you need to learn how to use your calculator to raise a general number to a general exponent. Do that, and it comes out that when you come back 10 years later, you will have $4,500 in there. That's the first part of the question. How much will be there? Second part is how much interest was earned. Well, the amount of interest earned is the difference between what you have and what you started with. So you have $4,500 and you started with $2,500, so the interest earned was $2,015.28. And remember, interest is dollars. So it hasn't quite doubled yet. But those are the calculations. Now the formula in this case, you're plugging in everything on the right-hand side and calculating the left. But you could plug in any place and be able to calculate. We're going to look at how would you solve that if you're plugging in somewhere else. We're going to look at that. But we could have asked, what's A, what's P, what's R, what's N, what's T? Any one of those we can ask, because they're different things, and there are different ways you approach it. Right now, we can't do some of those. Yes? That came from right there. Yeah, the compounding periods. How many periods per year is it compounded? And the normal ones would be once a year, 4 times a year, 12 times a year. There are a few that might be every day, although those aren't many. Probably a very few that's twice a year. Okay, here's one where we know what we want to have in the future, and we want to know how much we need to put there to have that much in the future. This would be the sort of thing you might want to do with a retirement account. I'm going to need this much money when I retire, so how much do I need to put in? Actually, you would need to do it based on a sequence of payments rather than a lump sum, but this is based on lump sum. The other is beyond this course. So what amount, if we put it in right now at 4.8% compounded annually, and you have to have all those different pieces. Today at 4.8%, so we need the interest rate, we need the compounding periods per year, we need the future amount, we need the number of years. All of those will let us then calculate P. So we know A, we know R, we know T, we know N. There's our formula. The only thing we don't know is P. But because we know all the rest, we can calculate P. Plug them in, and you wind up that 15,000 is 1.455 times P, divide by the coefficient, and you get P is $10,308.63. So if you invested $10,308.63 today at 4.8% interest, 8 years from now, you'd have $15,000. So very straightforward calculation, just plugging numbers in and solving for the one you don't know. A variation of that could be what if I only have $10,000? What do I going to have to do to get $15,000 in 8 years? Well, the only thing you really have as an option is what's your interest rate. So what interest rate would I need to have to make $10,000 grow to $15,000 in 8 years? So now we have A, we have P, we have T, we have N, and we have our formula, and what we're going to need to calculate then is R. That's the thing we don't know. What's our interest rate? So we plug the numbers in, and we wind up getting this. 1 plus R to the 8th power equals 1.5. This is one where in your calculator you also need to learn how to take roots of any level, because this is a situation where we have our variable completely inside this exponent. This is the only place R appears. So if we take the 8th root of both sides, we can get to R. So you need to learn how to do that on your calculator, taking roots of any magnitude. Take the 8th root of both sides, and you get R equals 0.052. So the required interest rate is 5.2% rather than 4.8. We really haven't looked at the final technique for solving this, where we have to start calculating the t. We're going to look at that shortly. But any of these other parts, you can solve for A, you can solve for P, you can solve for R with what we just looked at, just by the tools you already have familiarity with. We're next going to look at how would I solve it for the T or the N. Just as a kind of a historical note, that form of the exponential equation, that 1 plus 1 over n raised to the n power, if you look at it from as if you were investing $1 at 100% interest rate, then as you keep increasing n, this is going to get closer and closer to 1, but then I'm going to keep increasing how many times you multiply it times itself, and so it doesn't explode and it doesn't go to 0. What it does is it approaches a fixed number. As n gets larger and larger and larger, that result of, should be this, the result of increasing n without limit is that calculation will result in this number, 2.71828, and on and on and on and on, for an unending decimal. This number was encountered in several different places in science, engineering, finance, and various other applications, such that it was so commonly encountered that they actually gave it a name, and they call that number base E. And all your calculators have base E on them. You can look at E raised to the X power if you have a scientific calculator. That's based on this number being E. And it is a very useful number. It has a number of very friendly mathematical consequences associated with it, most of which you won't see in this level course. If you went on to calculus, you'd begin to see some of them. But it is very common, so common that it is included on all calculators. You can actually extend the concept of compound interest. We were looking at the situation where we had compounding once a year or twice a year or 4 times a year or 12 times a year or 365 times a year. What happens if you thought about just extending that infinitely? And that's called continuous compounding, where it's compounded, essentially every instant. Well, that reduces then to a formula of this type. You still have the A, you still have the P, but instead of the parentheses, what you now have is E raised to the RT power. That's where you get your interest rate, and your number of years in there is in the exponent of that base E. So $8,000, put it in an account at 5% for 6 years. If you compound continuously, and so you have to pay attention to the wording to make sure you use the right formula. What's the amount of after 6 years? Well, our P is 8,000, our R is 5%, and our T is 6 years. Put them into the A equals PE to the RT formula, and so you need to learn how to use the base E and raise it to a power. It's very simple. And you get 10,798. So 8,000 after 6 years of continuous interest is that. And actually, if you compared different compounding techniques, the more frequently it's compounded, the larger the number becomes. Continuous is the optimum, is the ultimate. That's the most you could ever get. Comparing that, let's take $1,000, invested at 4% for 10 years. If you only compound once a year, here's the formula, you wind up with $1,480. If you compound twice a year, looks like this. This is that compound interest formula we saw previously. We worked a couple of examples with. You get $1,485. 4 times a year, a little bit more. 12 times a year, a little bit more. Every day, a little bit more. If you did it continuously, just a little bit more. So it doesn't make much difference. The difference between once a year and continuously is only $11. But it does make a little bit of difference. Here's that function, a to the x. And here it is when the base of 2. So that's what the exponential function looks like, 2 to the x. That's this curve. It goes through the point 1 and a, 0 and 1, minus 1 and 1 over a. That's 1 over 2. That's 2. It goes through those points. What if I use a different base? What if I use a equals 3? Still the same sort of shape. It still goes through the point 0, 1. It now goes through 1, 3, and minus 1, 1/3. So it doesn't matter what my base is. It's always going to go through those points. And so that's what it looks like if you have a base greater than 1. What happens if the base is less than 1? It looks like that. It still goes through the point minus 1 and 1 over a. Let me get, oops, I don't want to do that. If a is a half, 1 over a half is 2, so it goes through the point minus 1 and 2, and it goes through the point 1 and 1/2, and it goes through 0, 1. So whether you have a base which is between 0 and 1 or a base that's greater than 1, you will always have this curve which approaches the x-axis on one side or the other. If the base is a fraction, the asymptote is approached on the right side. If it's greater than 1, it's approached on the left side. But it will always go through the points 0, 1, 1a, and minus 1, 1 over a.